Let's explore the second law of thermodynamics and show that entropy increases in a spontaneous process. The second law of thermodynamics states, there exists a property called entropy, S. The entropy of the universe increases in any spontaneous process. The entropy of a system is determined by the number of different ways to distribute the available energy over the various states of the system. The statistical mechanical definition of entropy relies on the number of microstates omega. A system approaches equilibrium by achieving the macrostate that maximizes the number of microstates. The proportionality between omega and S is given by the Boltzmann formula. Therefore, the equilibrium state maximizes not only the number of microstates, but also the entropy. This equation gives us an easily identifiable definition of entropy. Entropy is a measure of the number of states over which thermal energy is dispersed in the system. It also gives us a direct method of calculating the change in entropy, delta S, which is simply the entropy of the final state minus the entropy of the initial state. For any gas, the Sacca-Tetroda equation gives us an analytical expression for entropy of the translational degree of freedom, which is also the total entropy for a monatomic ideal gas. Otto Sackur and Hugo Tetroda proposed this equation independently in 1912. Interestingly, Hugo Tetroda was only 17 at the time he did this. The Sacca-Tetroda equation is one of the most important in thermodynamics. It facilitates an experimental test of the link between statistical mechanics and thermodynamics. It provides an independent experimental test of Planck's quantum hypothesis, and it demonstrates that the quantum hypothesis is applicable not only to massless photons, but also to massive particles such as molecules. The thermodynamic definition of entropy, it relies on heat, which stimulates disorderly motion. The heat evolved along a reversible path, Q rev, divided by T. That defines the entropy change and how to measure entropy, but not entropy itself. It does give us a mathematical formulation of the second law, ds equals dq rev divided by T. And so if we integrate, we can get the macroscopic energy change. It's important to note that statistical mechanics and thermodynamics lead to equivalent definitions of the change in entropy. They're not the same equations, but they are equivalent. So let's use thermodynamic to calculate changes in entropy. We need to evaluate this integral, but the question becomes, what is dq? Well, the answer is that it depends, because Q, the heat, is a path function, so it will depend on how the system evolves, what the process is. Now, the heat evolved at constant pressure under isobaric conditions. That is the enthalpy change. So if we have something like a phase change that happens at constant temperature, isothermal isobaric process, that is constant temperature, constant pressure process, then the entropy change is simply delta H divided by the temperature at which that phase transition occurs. For simple heating, well, it's the heat evolved is simply the heat capacity times dT. But if we have constant pressure heating, we have to use Cp, the heat capacity at constant pressure. And if we have a constant volume pressure, we use Cv. And if the heat capacity is constant, well, we can pull it out of the integral, and that leads to this very simple equation, delta S equals the number of moles times the heat capacity times the natural log of the ratio of the final temperature, T2, to the initial temperature, T1. If we have an isothermal expansion or compression of a gas, we get a very similar expression for delta S. The entropy change is equal to the number of moles times the gas constant times the natural log of the ratio of the final volume to the initial volume. What if we have a process where both temperature and volume are changing simultaneously? Do we need a new equation? No, let's think about this. Entropy is a state function. It doesn't matter how we get from state 1 to state 2. It just matters that we got there. So we can break up the process into two known steps. We'll break it up into an isochoric step, where the volume is constant and we just do heating, changing the temperature. And then the second step will be an isothermal step, where we change the volume and expansion or compression in the second step. So if we know the answer for the isochoric process and we know the answer for the isothermal process, when we change both, do we need a new equation? No, we don't need a new equation for this different process. We can use the two equations that we had for the individual steps and just add them together. Now, what about this conclusion in the second law that the total entropy must increase in any spontaneous process? Let's put a gas in an isolated container at some initial pressure. We know that it never spontaneously compresses itself. The only way to get a gas to go to half its volume would be to do work on it, to increase the pressure by a factor of 2 by doing work on the system. The system will never do this on its own, even though the internal energy change is 0. So let's think about the reverse process, the one we know occurs. We put a gas in half a container and let it expand, and indeed it will spontaneously do this on its own. We don't have to do any work on the system. It will spontaneously expand to fill the entire container. How can we calculate the entropy change? Well, let's put a monotonic ideal gas in, say argon, right? We can use the Sacca-Tetrode equation to calculate the entropy of the initial state, calculate the entropy of the final state, which have two different volumes, take the difference between the two, and we'll get the entropy change of the system, which is a positive number. Now, the system is isolated. There's no heat flow to the surroundings. If there's no heat flow to the surroundings, the entropy change in the surroundings is 0. So the total entropy change is now the sum of those two terms, and it is indeed, again, a positive number. Now, it turns out we can generalize this to any system and state that for any irreversible process in an isolated system, there's a unique direction of spontaneous change, delta S greater than 0 for the spontaneous process. Now, if we take the isolated system to be the universe, for as far as we know, the universe cannot exchange matter or energy with anything outside of it. Therefore, we can state for any process, a spontaneous change corresponds to one in which the total entropy change of the system plus surroundings is positive. Now, a system can change spontaneously and have its energy decrease. But for this to happen, the concomitant change in the entropy of the surroundings has to be sufficiently positive such that the total entropy change of system plus surroundings is positive.